Hello everyone, so welcome back, and in this specific video series we are still tackling CNN architectures, and we are going to deal with Mobilenet, the architecture which was a state-of-the-art model which was implemented for mobile devices. So essentially it was an architecture which essentially did exemplary on low computing devices, and hence why we are dealing with it now. And also it has also been used in as the base architectures for even YOLO algorithms, which are one of the object detection algorithms that we are going to deal with later on when we are starting the series on object detection. So thank you, and let us begin on the implementation and on the discussion around the Mobilenet architecture. So I'm going to implement it uses TensorFlow. So I'll import also this custom file that we'll need for visualization. So then we import the layers that we need. So one of the operations that was being done on the Mobilenet architecture was the depthwise convolution. So depthwise convolution, it essentially did the convolution operation channel-wise. So instead of passing like the filters across a 3-channel image, it essentially split the image into 3 channels, and then the convolution operations were done on the channels separately before concatenation was done, and then the output sent to the next operation in the architecture. So we look at it later in the inverted residual. So the Mobilenet worked with an inverted residual as its base block, and it's also used ReLU 6 activation function as opposed to the normal ReLU that we're used to. So first let us see how the inverted residual was. So it has 3 layers, and as in the case of most other architectures that we've handled, each layer was accompanied by a batch normalization and a ReLU operation. So for instance, the first layer was conv2d 1 by 1, so it's accompanied by a batch normalization, after which we see a ReLU 6 operation. So ReLU 6 operation, as opposed to the normal ReLU where the negative values are normalized to 0 and then the positive values are left as it is. In this case, for positive values exceeding 6, they are normalized to 6. So we see that ultimately the output of the ReLU operation, in our case for the Mobilenet, was between 0 and 6 and in between, not any other value. And then we see that the inverted residual essentially had a convolution. So we see that it's a convolution, a batch normalization, and a ReLU 6 activation function. Then in the middle layer, we see a depthwise convolution, which we said is a convolution that acts on each channel as it is. So after acting on each channel, it's concatenated, then passed through a batch normalization through a ReLU 6 operation. Then the last layer we see essentially is a linear layer, meaning that it has no activation function in the output. So it only essentially add a convolution and then a batch normalization. Then apart from the flow of the inputs through the layers of the inverted residual, we also see something, a variable t known as expansion factor. So this expansion factor was multiplied by the input filters in order to achieve the output filters for both the first for the first layer of the residual block, essentially because the depthwise convolution essentially retains the number of filters that has been received in the input. The only difference we see that the depthwise convolution reduces the resolution of the images by a factor, which in this case is the stride, which will be passed through the depthwise convolution layer. Yeah, so that is all on the inverted residual. So this is an inverted residual. So here we see an inverted residual, but then we'll change in when we'll be implementing now the linear bottleneck class. So this one is now considering it with the normal ReLU operation here. So we see convolution, then batch normalization, then ReLU operation, then the depthwise convolution, batch normalization, then ReLU. Then lastly we see convolution, batch normalization. So now to achieve this block, the residual block for the Mobilenet, first of all we'll multiply the last shape of essentially the input filters. So we extract the shape of the inputs to get the number of filters of the input. Then we multiply it by an expansion factor T that we'll put here. Then after that we'll remove the last ReLU operation, essentially, because we see that the last layer does not have an activation function, and then the ReLU operations will replace them with a ReLU 6 activation function, which is found inside the tf.nn module. So this is our inverted residual. Now we see that the residual block that we'll achieve will have a ReLU 6 activation in the first layer, then a depthwise convolution with kernel size 3x3, ReLU 6 also. Then the last one has no activation function, hence the term linear in the output. Then after that we take a skip connection, and then in this case we don't sum it, we concatenate it. So there's difference between this one and the previous ResNet and ResNext that we have discussed. In this case scenario, we don't add, but we concatenate the output of the skip connection and the output of the linear flow of the residual block. So when we implementing the linear bottleneck now, we see that we take the filters, the number of filters of the input, we multiply by the expansion factor. Then after that we'll pass it through a batch normalization and then a ReLU. Then after that we'll pass it through a depthwise convolution, then a batch normalization, then a ReLU 6. Then finally the last part, so we've seen this one and then this one. Then the last part here we have a convolution one by one. We have a convolution one by one kernel size, then output which will be specified here. Then we also see that the skip connection, the input when passed through a skip connection will pass through a conv2d of kernel size 1 by 1, and then we see that after now instantiating the layers that we will implement in the call function, we see a convolution, batch normalization, then ReLU 6, then we see a depthwise convolution, batch normalization, and ReLU 6, then we see lastly a convolution. So Sorry about that, it was essentially not concatenation, but it's still a summation block. It's still a summation block. I think it's the dense net architecture that has the concatenation block, not the mobile net architecture. So sorry about that. So this one now is the residual block, known as the linear bottleneck for the mobile net. Now that we've looked at the inverted residual and the linear bottleneck and also the ReLU6 operation, which are the core of the mobile net architecture, we want to now implement the architecture in itself. So we see that this C is the out argument which we will be passing through the linear bottleneck. Then T is the expansion factor. Then N is the repetition of the blocks. Then S is the strides. So we see that essentially this scenario, I put it inside this list of dictionaries. We see that it's essentially the same. For the first one, it's input, and then there's no expansion factor, output is 32, the repeating is 1, stride 2. So I've essentially summarized this one inside a list of dictionaries. Then I'll now try to create the mobile net architecture. So we implement an empty list. Then for the input, which you'll see that it's only repeated once. In short, there's no repetition. Sorry, there's no repetition. So we see that for the input, it's 32. Then kernel size 3, strides 2, padding same. So this is for the input. Then this one now is for the implementation of the linear bottlenecks within the mobile net architecture. So we see that if we view the mobile net architecture, we see that this one is for the implementation of the input layer. Now I want to start dealing with the bottleneck architecture, this one, all the way up to here, after which we'll finish off with the convolution 2D, then average pooling, then convolution 2D. I think for my case, the last part I implemented it using dense, but you can change it. So you see that the expansion factor is also always applied to the input size, as we had seen earlier, where we extracted the last value of the shape of the input size, and then we multiplied it by the expansion factor in order to get the output filters of the first layer of the residual block in our mobile net architecture. So essentially, after instantiating the input of the mobile architecture, now we want to deal with the bottlenecks. So for the number of repeating patterns specified, we want to loop through the repeating bottlenecks that have been specified, and then we append it to the layers. So after the input, we append the bottlenecks in the repeating that is required here, and then we'll be finished with the linear bottlenecks. So this statement here essentially is this one. So the first layer of each sequence has a stride S, and all others use stride 1. So this stride 1 is all other layers, and except for the first layer, which we see that for if I is 0, so for the repeating bottlenecks, for the first layer of that repeating bottleneck, we'll have a stride of 2. In this case, S will be now 2. Else, now for all other layers except the first layer, we see now the stride now being initialized to 1. So that's what we implemented there. So we implement. So let me look at the error for a while. Okay, so the error is specifically because I have essentially, when we come back here in the linear bottleneck, essentially we are referring to the input, yet this one is only seen in the call function. In the initialization function, there's no input shape that we can infer from. So the workaround with that is to use the build function. So say self, then we get the input shape. So the build function essentially is a special function that helps us to infer the input shape. So it essentially gives us the advantage of late variable creation based on the shape of the inputs that the layer will operate on. So after that, now what I do is I move this layer under this one so that I'll get the expansion factor, then I'll multiply it by the input shape. So and then after that I also enable the expansion factor to be visible by the input shape. So then I'm done. So when we again go through the implementation, we've implemented the input, then the bottlenecks. Now it's okay. So after that, after implementing the bottlenecks, I implement so after implementing the bottlenecks with expansion rates 6, all of them, I implement the conv2d one by one, which I see here. Then after that, we see that after the conv2d one by one, we go to the average pooling. So after the conv2d, I go to the average pooling, which for my case I've used the global average pooling. Then the last layer I have used the dense layer with my case the dense layer now will have an output of 1280. So as we can see, the output is 1000. I used 1000, so the dense layer output is 1000. Then now we will want to extract the layers from the list and build the model, now the Mobilenet. So this one, let alone this one. So after now building the Mobilenet model, we can have a summary of our Mobilenet architecture. So this is how we can implement the Mobilenet, specifically version 2 architecture, considering the inverted residuals, the Residual 6 activation function, and the linear bottlenecks. So thank you for watching, and I'll see you in the next video.